Benoit and Peter for organizing this fantastic workshop. I really had a fun time, especially listening to all the historical tidbits. What I thought I would try to do to fit with this theme is talk about progress that the community has made in a fairly difficult problem. I mean, it seemed like it wasn't going to be a difficult problem, but the problem of adding intentional impurities or dopants to quantum dots. So in some sense, my title here could be called The History of Our Inability to Dope, because we've had lots of challenges over the years, as many of you know. And I think over the years, though, we've started to develop some understanding and some progress in this area. Now, of course, any atomic impurity could be considered a dopant if it changes the properties, but I'm going to focus on the motivation of electronically active impurities, so impurities that can add extra carriers. So I think the motivation then is clear. So we know how we control conductivity in silicon with things like phosphorus and boron doping. And we have films of nanocrystals that we want to control the conductivity of because, as we know, many applications, we have to get electrical current either in or out, and they don't conduct very well. So the obvious question is, why can't we do impurity doping instead of some of the other tricks that people have developed to get around this problem, and do N-type or P-type doping with donors and acceptors, respectively. Now, beyond this, there are, of course, also fundamental questions beyond that applied motivation. So we know that we have the possibility of squeezing this impurity in a very small volume, and so there might be quantum size effects. There might be new physics due to all kinds of aspects, not just of squeezing a donor or acceptor, but things that we haven't thought of, overlap integrals and things like this. Now, unfortunately, as I've already alluded to, there have been a lot of problems. And so most of the early attempts failed, and by early, I mean early 90s or before. And most of these attempts weren't even reported. So you just ask anybody that was making nanocrystals at that time if they tried any doping, and they all tried doping, as far as I can tell. But if you think about it, they had lots of problems on their plate as it was. The synthesis, of course, was not already developed, as we've already heard. And so if they didn't see something interesting immediately, they moved on and they focused on some of the other problems that they had in front of them. Now, some of the issues that you have to deal with are really kind of banal and frustrating. So one of them is if you want to synthesize something like this, impurities in your nanocrystal, of course, you could also get this. And you have to have characterization techniques to be able to distinguish between these two. And this is not a trivial thing if you think about it. Even if you do succeed in making your nanocrystals that have impurities in it, you have all the distributions you have to deal with, not just size and shape that all of us have to deal with if we make nanocrystals, but also fluctuations in the location, whether it's in the center or on the edge. And Sasha, in this paper from 1990, already pointed out the effect of position on donors and acceptors in nanocrystals. And also a trivial thing like the number fluctuations of impurities. So if it's Poissonian, you have one on average. That means a third of your particles have no impurities. A third have one, and a third have more than one. So you can imagine that that's going to affect your properties if a third of them have none and a third of them, or two-thirds have one or more. Now, doping was discussed from the very beginning. So even in Lewis's famous paper here in 1983 that he discussed, he talked about doping kind of as an aside in two contexts. One was in terms of charging, and of course there's a relationship between charging and impurity doping. And we've already heard this in a couple of different talks, that they were looking at the ionization potential, so the energy that it's required to rip off an electron and leave behind a positively charged nanocrystal. And it's going to be important later for my talk to remind you of something that Lewis told us on Monday, that if the dielectric constant of the nanocrystal is larger than the surroundings, this positive charge here will be repelled from the interface because, well, you can look at it in terms of a dielectric polarization, or as Lewis explained, in terms of a physical chemistry picture of charge solvation. So this positive charge is best solvated by the dielectric when it's sitting in the middle. And the other thing that he mentioned in his paper, just as an aside in one sentence, he gave a feeling of why doping might be difficult in quantum dots. And the sentence was that he assumed that the crystal light was sufficiently small that it wouldn't have any dopant atoms. And so this was a very common statement that people would make. And I'm going to explain it in terms of a Turnbull model. So David Turnbull, who is a physical chemist, but one of the fathers of material science, he just died a few years ago. In crystallization, in the context of crystallization, he came up with a model that we could apply in this way to nanocrystals. So imagine you have a bulk crystal that has a certain solubility of impurities. He basically argued that if you divide this up into smaller and smaller pieces, eventually none of the little crystallites will have any impurities, assuming that you keep the solubility of the impurities the same, a number of impurities the same. So the argument goes that if the size is small enough, you don't have to worry about dirt in your nanocrystals, so they'll be pure. And this is a purely statistical model. There's no new physics. It has to be true at some level, but it assumes that the solubility is the same in both cases. Now, like I said, it has to be true, but it can't explain some of the problems that I'm going to discuss in a minute. So below all the examples that we'll touch on, all treat dopants where the solubility is sufficiently high that I could easily have one or more impurities per particle, right? So this model assumes that the solubility is low enough that you can make the particle small enough to have less than one impurity. Now, another very common model I'll mention this in a minute. This very common model is self-purification model, which has been very alluring over the years. And it argues the following, that if I have a nanocrystal that has an impurity inside of it, it's always just a few lattice constants from the interface. And so if there's any kind of thermodynamic driving force to push that impurity to the surface, that will happen, and the particle will self-purify, and you'll squeeze out this impurity. Now, this idea has been around for a long time. I could not find, I've looked a lot, and Sasha looked a lot. This was the earliest paper that we could find that mentioned it in print. But if anybody else knows about another paper, I would be very happy to hear about it. So this is a thermodynamic model. It requires diffusion, right? So this impurity has to diffuse to get to the interface. If it doesn't diffuse, this model can't be applicable. And it also requires new physics, because if the formation energy of this impurity in the bulk material is sufficiently low that you can dope the bulk, then this implies that the formation energy is going up in the nanocrystal, and that's what's driving it out. And there had been some reports, theoretical reports, that the formation energy did go up with decreasing size. Okay, so the question now is, does this self-purification model explain the early difficulties people were having? And one paper I'd like to point out, I think it's a really underappreciated paper here by Alosha and Sasha in 1990, where Alosha had made cadmium sulfide quantum dots in glass, as we've heard about, and at low temperature, when the particles were large, they saw very complex photoluminescent spectra. So they had, this is the band edge peak, and then they had all these other lines, and they assigned those to donor and acceptor transitions. And they speculated, I mean, it's still not known what these lines, as far as I understand where these lines come from, but they speculated in this paper that they're due to impurities and or defects. Now, for the self-purification picture, this seemed to support self-purification, because as the nanocrystals here are large, 700 angstroms in radius, but as they went down to more typical nanocrystal sizes, all of the structure here disappeared, and they only saw kind of this, quote, deep trap emission that we often see at low temperature in nanocrystals. And so this seemed to suggest that the impurity lines that were maybe due to impurities were disappearing at small size due to this self-purification model. I also want to point out that in the same paper, Sasha worked out the theory of donors and acceptors in colloidal quantum dots, and so how the donor or the acceptor changes its properties as a function of radial position, and so there's a lot of useful things in this early paper. Now, the next step kind of in the story is that there was a paper in 1994 by Bhargava et al. In PRL that really caused a lot of excitement, because it was an example of successful doping, not an electronically active impurity, but manganese as the dopant. And so in this paper, they made 3 nanometer zinc sulfide nanocrystals, and they proved by several different techniques that the manganese was incorporated. And why it was interesting is that these particles, if you excited them with light, without the manganese, you didn't get any photoluminescence, so they were very poor particles in terms of their inherent photoluminescence. But with the manganese, you got very efficient energy transfer to the manganese, and then it fluoresced in the red-orange through an internal transition of the manganese. And so you had this very efficient transfer, and the reason, energy transfer, and the reason it got everybody excited was that the fluorescence quantum yield was really quite high. It was reported to be 18%, which if I remember at that time in '94 was the highest fluorescence quantum yield of any particle, doped or undoped. So it really started to make people think about what the possibilities of doping might be. And moreover, they claimed in this paper that the lifetime of this transition, which is partially spin forbidden, so in the bulk it's 2 milliseconds, a very slow transition. They claimed that the fluorescence lifetime in the nanocrystals was 5 orders of magnitude faster. And this got everybody excited that this was unexpected and this was new physics. Unfortunately, our chair here, Andres, and his student proved a few years later that this was an artifact. And so the lifetime was actually just as slow as it was in the bulk. But in some sense, the train had already left the station, right? So people were already excited about all of this stuff and started making people think about it. And the fact that this second exciting thing was not true didn't seem to affect that at all. So this generated a lot of interest. But these nanocrystals were made by a room temperature co-precipitation. So this was used using a very simple synthesis. And so it tended to yield what we would call now low-quality nanocrystals. So for example, it didn't photoluminesce. And so the question was, can we now start applying these new syntheses that had been developed and generate even better doped nanocrystals? And this led to manganese being used a lot as an impurity, and in particular a model impurity. And manganese is really nice as a model impurity because you can use electron paramagnetic resonance, or EPR, to really locate where the manganese is. So I mentioned that it's very difficult to find techniques to determine where the impurities are. But with EPR spectra, so I'm showing 2 typical EPR spectra here, you can very clearly distinguish spectra where the manganese is on the surface or on the interior or inside the lattice of the semiconductor. And this is because these EPR spectra are governed by hyperfine splittings between the nuclear spin of the manganese and the electronic spin. And this hyperfine coupling is very sensitive to the local environment. And so, and of course, most universities, somewhere, maybe in a basement, there's an EPR spectrometer. So you can go and easily do these measurements and determine where your manganese was. And so using manganese, even though it's not electronically active, as we'll discuss, the doping process could really be studied and understood. And so what the Buendia group did in the 90s was do what I just posed, is try to take these newer synthetic methods and try to improve the doping of dots. And so they took the cadmium selenide prep and they added some manganese precursor, and then they did a lot of very careful characterization to figure out where the manganese was. And they always found that the manganese was excluded from the particle, or was not incorporated, let's put it that way. And so again, the question arose, was this due to self-purification? Because the Bargava work was done at room temperature, so diffusion might not be so active. This is grown at higher temperature, maybe diffusion starts to be active, and so this might be the reason why self-purification, why doping doesn't work, due to self-purification. And if you started looking at all this data of manganese doping that was occurring in the late 90s, you could kind of see it through that optic in the sense that papers reported that you could dope manganese if you grew the nanocrystals at low temperature, but of course we would like to prove that by growing at higher temperature. But when you tried that, according to this paper, it didn't work. It turns out it was just luck, dumb luck in this case. And then at the same time, in my group, we were playing with zinc selenide using a synthetic procedure that was developed by Peggy Hines and Philippe Guillot-Sienet's group. So they had developed making zinc selenide. And we added some manganese, and we did careful characterization, and we showed that the manganese was incorporated. And so this was kind of confusing because these were very similar growth reactions, so zinc selenide and cadmium selenide, but by luck, I mean, they used different surfactants. So topo was used for cadmium selenide, so trioctophosphine oxide. It turns out to be bad for doping. And in this prep, you use hexadecylamine. And it turns out that that affects the kinetics of the doping, as I'll mention. But anyway, so what's the explanation in the broader term? So why could we dope zinc selenide and not cadmium selenide with manganese? So after a lot of work with Steve Irwin, who does density functional theory at NRL, Lijun Zhu, a very talented synthetic student of mine, and then Sasha Efros and Tom Kennedy, we came up with a model that we thought could explain all of these disparate results. And instead of using self-purification, which again is a thermodynamic model and requires diffusion, we thought about kinetics. So if you want to try to get an impurity in this growing nanocrystal, there's several things that you require. So of course it's surfactant coated, but to grow we know that the surfactant has to be popping on and off. And so our impurity atom can come in this cartoon and stick to the surface. And if it stays there long enough, then it can be overcoated with more material. And if diffusion is not active in this limit, then it's basically going to be stuck where it is inside the nanocrystal. And so in this model, the kinetics really dominates the doping. And it's interesting to think that just like molecular beam epitaxy, this would imply that the solubility of the dopants can be either higher or lower in principle than in the bulk, because kinetics is in control, not thermodynamics. Now, if you didn't like that example because it's at low temperature, maybe self-purification really is going on when diffusion is in control, high temperature growth. There are other counterexamples that rule out self-purification. So the Fuji group at Kobe University has done a lot of work since '96 on growing silicon nanocrystals inside an oxide film. So these are grown by sputtering and then annealing at very high temperatures, 1100 C. And the diffusion is obviously very fast in these samples. And they showed that you could get both phosphorus and boron doping. And they've done a number of papers, maybe 20, 25 papers since this '96 paper on all the properties of these doped particles. And it's also been confirmed in gas phase grown silicon nanocrystals more recently, like in plasma and other things, that they could dope with phosphorus and boron. So the bottom line is that, as far as I know, there are no known experimental examples of self-purification. So if anybody has an example they want to share with me, I would really like to know it, because I can't rule out that there's such a model, such a process, but as far as I know, there are no known examples of this process. And with effort, we can overcome all the doping difficulties as long as the impurity has sufficient solubility. So we have these two problems. We have thermodynamic or two limiting models, so thermodynamic or kinetic limits, where you either have fast or slow impurity diffusion, but we have successful examples of doping in both limits. And moreover, there's been a controversy over this report that I mentioned, that the formation energy of the impurity, the defect formation energy, increases with decreasing size. So that was reported here by Jim Chelikowski's group. And Steve Irwin, who I was collaborating with, did a huge amount of work to try to reproduce those calculations using all kinds of different codes, and they could never get it to increase with decreasing size. So I'm not an expert in that, but it's still very controversial. Even if it were true, though, we have to keep in mind that in the examples, like the manganese examples of nanocrystals grown at relatively low temperature, a few hundred degrees, kinetics is in control anyways. So diffusion is not that active, and so it would be hard to imagine that this self-purification idea would be active. Okay, so because of this, there was a lot of progress made in doping in the 2000s, early 2000s. And if we think about it, though, it was all substitutional, or mostly substitutional and magnetic impurities. So things like manganese and cobalt, the example that I gave, so manganese doped into cadmium selenide. And obviously, you're replacing some of the cadmium 2+ with manganese 2+ on the lattice. And although there are lots of interesting optical and magneto-optical properties that have been reported and will continue to be reported about these systems, in particular manganese is both an optical and a magnetic impurity. Even though all of this is going on, it's still a dopant that's replacing an isovalent host atom. So if our goal is to do electronically active impurities, then this isn't going to get us there. So we have lots of reasons why we might think that it's worth trying to get there. And so Philippe just talked about the experiments that he did on the charged nanocrystals. So by either reducing a nanocrystal and injecting an electron, putting it in the conduction band, or in some later papers, as he just told us, you can electrochemically reduce a film of nanocrystals and put electrons. You could get orders of magnitude increase in the conductivity. So this is kind of a motivation that, why can't we do this with electronically active impurities? Now, I do want to stop, though, and mention that although there's clearly a relationship between charging and impurity doping, there are also differences. So if you charge a nanocrystal or reduce it, you're just putting an electron on the particle, or you can take it back off. If you have an impurity there and it ionizes, now you have your, in this case, if it's a donor, you have your electron and you have your ionized impurity center left behind. And as we might expect, this electron can go off and do all kinds of bad things. It can reduce something in the environment and leave. And then we're going to be left behind with this ionized impurity. And that can also affect potentially the properties of the nanocrystals. So we have to think about the fact that we can have ionized impurity centers, and that's going to be important in the last part of my talk. But it also points to the role of the host semiconductor for holding on to these extra carriers. And so there was a very early example of N-type doping of nanocrystals done by Celso and Andres quite a few years, or 10 years ago now. And it was lithium interstitials and zinc oxide. And zinc oxide is known to have a very low conduction band edge on an absolute energy scale. And so this electron that's sitting in the conduction band, we can consider it that it doesn't have sufficient reduction potential to do a lot of bad things potentially. So the choice of the host semiconductor can also play a role here. Now, I want to kind of transition now from kind of a historical talk to more recent work and give you a feeling of what's been happening in the last few years on electronically active impurities. And so one paper I want to highlight, and already mentioned it, was this collaborative work between Milo Rabbani and Benin and their students, where they took an indium arsenide nanocrystal, as we heard about yesterday, and they put copper, silver, or gold impurities into these indium arsenide nanocrystals. And then they parked their STM tip over the nanocrystal and looked at electrical current as it was going through the individual particles. And looking at the change in current with voltage as a function of the bias between here, they could detect the valence band edge and the conduction band edge. And this was shifting dramatically depending on which impurities they had. And they explained these shifts as silver being a p-type dopant and copper being an n-type dopant. Now, one thing that we wanted to do to complement these results is that these were in the heavy doping limit. So they had tens to hundreds of impurities per nanocrystal. So my cartoon here with 14 impurities is on the low end of the limits that they were looking at. And so we wanted to look at light doping. And I'm putting light in quotes because even one impurity per nanocrystal is already in the high doping limit in the bulk, just because of the volume that each impurity will occupy will still be quite high in a bulk sense. But we can't go any lower than 1, right? So we're going to have to call it light doping. And then we also wanted to look at cadmium selenide instead of indium arsenide because, of course, we know so much about cadmium selenide that if anything changes, we should be able to detect it. So then the question is, how are you going to incorporate the impurities? And to avoid all these kinetic problems, we started looking at this process of cation exchange to do the doping. And so we heard yesterday about, from Rahman, that this idea of cation exchange that was introduced by the Alivisatos group, where if you take cadmium selenide nanocrystals and expose it to some silver cations in solution, they very rapidly completely convert to Ag2Se, so silver selenide. And they tried to slow this down, actually for doping. So Richard Robinson told me that when they were doing these experiments, they were trying to do doping. And this process was so efficient that even if they tried to stop it kind of midstream, they just got phase segregated, in this case nanorods, where they got stripes of silver sulfide and cadmium sulfide rods. So the process was super efficient, and so the question that we were trying to address is, can we really slow it down enough where we can get to this doping limit of 1 impurity per nanocrystal? And so this turns out this is possible. So Ayash Sahu, a PhD student of mine that just graduated about a year ago, he found that it was fairly straightforward to basically dial in the number of silver impurities that you want per particle by adding some trioctophosphine. So this surfactant presumably mediates the incorporation. And so by doing elemental analysis, he could basically measure the number of silver per nanocrystal on average as a function of the amount of silver, and you could just dial in the number that you wanted. Now, to make sure there wasn't anything going on in terms of phase segregation, he looked at the absorption spectra as a function of the number of dopants, and nothing really changed. We'll talk about that in a minute. And the X-ray diffraction, nothing really dramatic changed as you went up in the number of silver impurities. So he was able to get to this lightly doped limit. Nothing dramatic was happening in absorption or X-ray diffraction. But a really key thing about this approach is that it's extremely easy to obtain an entire doping series now. Because if you try to add in some silver while you're growing your cadmium selenide particles, just by adding the silver, of course, you affect the growth and the shape. And so it's very difficult to make a series of samples that are all identical in a typical reaction, but have a different number of dopants. And so by using cation exchange, it's very easy to do that. You just make a big batch of these, and then you introduce portions of it to different amounts of silver. Now, what would we expect from silver? So silver could be a substitutional acceptor. So if it swaps out for cadmium, it has one less valence electron, and so it could introduce a hole here and be p-type. Or it could be interstitial. It's known to be a fast diffuser in cadmium selenide, so it could be diffusing through the interstitial sites, and so then it would be a donor where it would give its extra electron to the lattice. So what do the experiments show? I'm not going to show you all the experiments due to time, but I want to show you one of the really puzzling things. One of the first things that Ayash saw is that he saw a dramatic enhancement in the photoluminescence with doping. And so here is the photoluminescence spectra of these cadmium selenide nanocrystals undoped. And it's not that it's weak. I'm just normalizing it to 1 because it's going to get a lot bigger in a second. And then on the right here, I'm plotting the peak of this PL line as a function of the number of silver nanocrystals. So this is the undoped sample. And when he just added 2 silver on average, so just kind of a whiff of silver to the nanocrystals, the fluorescence intensity went up by a factor of 10. So going from 0 to 2 on average. And then as he kept going, it came down when he went to 4 and 12, but always above where it started. And I didn't believe this at first because, as we've already heard, if you put an extra carrier, you have the possibility to quench the photoluminescence due to Auger. So he did it on many different samples, many different sizes. It always peaked at about 2 silver impurities. And moreover, I mean, these are not great dots. So these are just core dots, so they have a fluorescence quantum efficiency of a few percent. But after adding silver, we measured it's about 30%. So this is starting to become comparable to a core shell, but just by adding 2 impurity atoms. So in addition to that strange result, we did a lot of experiments, which I'm just going to summarize here. So Ayash and another student, Moon-Sun Kang, did optical, electrical experiments, and then with Marcus Vintera's group in Germany, we did XAFs. And all of these results were consistent with the following kind of non-monotonic behavior. So at low concentration, silver was acting as an interstitial donor. At higher concentration, there seemed to be, and higher concentration means about 5, something on order of 5, silver transitioned to a substitutional acceptor. And this could explain all of this, these results that I'm not showing you. But it still leaves a few questions. So one question is, if we really have electronically active impurities, then if I'm putting carriers into the conduction band, for example, as Philippe just showed us, we should have a bleach in the absorbance. And we don't see any change with increasing silver in terms of the absorbance. So it suggests that there are no free carriers in the dot. And then the other thing we really need an explanation for is why we're getting this very bizarre effect of this big boost in the photoluminescence with just a couple of silver. And so to try to address this, we started working with Steve Irwin again and trying to develop a microscopic model that can explain all the data. But not just our doping data, but also the broader question of how cation exchange works. Why is cation exchange so fast? What's going on a microscopic level to explain this process here? And I should mention, it was already mentioned, I mean, cation exchange is becoming increasingly important because it's a route, as is pointed out in this Mana paper, it's a route to take materials that we know how to make really well and convert it into new materials without having to do all the hard work of redeveloping the syntheses. So it's becoming important, and we should understand it. And so our model should explain the doping results, the speed of the cation exchange reaction, and also this data from the Alvasados group where they tried to freeze the cation exchange again early on, and they saw these little seeds of silver sulfide that were nucleating on the surface of these nanorods. And so our model has to try to explain all of these different results. And so to get at this, I have a PhD student, Florian Ott, who's working with Steve Irwin, and he started doing density functional theory calculations for defects in silver defects in cadmium selenide. And there are two defects, like I said before, that we have to consider: the interstitial and the substitutional. And the calculations show that an interstitial is a shallow donor. And so if the Fermi level is somewhere mid-gap, then that electron will fall to the Fermi level, and this interstitial will become positively charged. That's what the calculation showed. And then for the substitutional, it was a deep acceptor. And again, if the Fermi level is mid-gap, electron will fall into it, and it'll become negatively charged. And all of this is kind of consistent with what we would expect. So we said we thought interstitial would be a donor, and this also agrees with old bulk literature data for silver in bulk cad selenide. Okay, now one thing that we didn't really appreciate at the beginning, but turns out to be everything in cation exchange, is if you now have ionized impurities. So we have, let's say we have these two positively charged silver interstitials. Of course, they're going to interact by Coulomb interactions. And that would happen in the bulk, but of course we all know that if we now squeeze them inside a nanocrystal, that these interactions are going to be even stronger. And on top of that, I told you about Lewis's old ideas about charge solvation. These will be repelled from each other and from the surface. So this is all of these Coulomb interactions between the charged impurities turn out to be everything. And you can model the repulsion from the surface by image charges, and so you can do all of this quantitatively. So these Coulomb interactions play a major role. In fact, cation exchange would not happen without these Coulomb interactions, as I'll try to show you in the last few minutes here. So two examples of why these interactions are important. The first one is interstitial diffusion. So I told you silver is a very fast diffuser in cadmium selenide. So you can calculate the diffusion barrier of this interstitial hopping from interstitial site to interstitial. And the barrier is about 0.2 eV. But if you have any Coulomb interactions, of course, this will warp this potential energy surface. So for example, if you already have a substitutional silver that's negatively charged, then this barrier, as this thing diffuses, will get smaller and smaller as this thing gets sucked in towards this negatively charged substitutional. So that's one example. Basically, diffusion will occur quickly towards a silver interstitial will move towards a silver substitutional. And the other important example is cation exchange will not occur without this reaction. At some point, a fast silver diffuser, an interstitial, has to kick out a cadmium to form a substitutional silver. And if you do the calculations, the barrier of this is enormous. So it's 0.65 EV. And this is way too high to explain cation exchange. Cation exchange would be extremely slow if this were the only mechanism that were going on. But if you now add the premise that you already have a substitutional silver that's negatively charged, this can help stabilize all of these ions, all these charge, and you can lower the barrier by 0.25 EV, and this speeds up the reaction by 4 orders of magnitude. And so just this cation exchange, this Coulomb interaction here can explain cation exchange. So cation exchange really relies on these interactions, and I'll show you that in a simulation right now. So Florian and Steve did these kinetic Monte Carlo simulations to put all of these calculations together. So this is an interstitial silver inside a nanocrystal, and you can figure out at each step of the simulation what the possible reactions are and what can happen. And so here it is diffusing around inside the nanocrystal, and it's being repelled by the barrier because it's positively charged. And if you look here, this is the radial distribution of this silver. And as we add more, they have to repel, they have to keep away from each other and the surface. So the average position of these cations will shift towards the surface as we add here a third one and then a fourth one in this simulation. So we're just slowly adding silver into the particle, and eventually they get pushed out towards the surface that one of them gets close enough that it does one of these kick-out reactions, and it immediately attracts interstitial silvers and starts to nucleate a little Ag2Se phase. And if you speed this reaction up now, you can just see that as you add silver, it basically starts to grow on the surface, just like the experiments seem to suggest, this new Ag2Se phase. And that by the time the simulation here is finished, if we look out here on the surface, this gray line is the number of interstitial silvers, and the dark line is the number of substitutional silvers. And these are nearly in balance, which of course is what you would expect from an Ag2Se phase. Now it turns out this simulation that I just showed you will explain all of the results. So it'll explain why it's N-type doping at the beginning, because you have these interstitial silver that are keeping away from each other. And it also can explain why it goes P-type as you get more and more of the substitutional. Okay, the last thing I want to mention, though, is why the enhanced photoluminescence. So at low concentration, so 1 or 2, the model and all the data suggests that silver is interstitial donor that leads to an ionized impurity. And so we have something like this, and it ionizes, so we now have this positively charged interstitial. And the model is suggesting that for some reason, and we have ideas about how this works, but we're not ready to talk about it yet, but for some reason, this positive charge makes another electron hole pair recombine more often. And so this would be consistent if the electric field of this positive cation confines the electron a little bit more, right? If it's really going on, we should see a blue shift in the photoluminescence, and that's exactly what we see. Even adding 1 silver on average, we see a clear blue shift in the photoluminescence of the particles. So this all of it seems to suggest that an ionized donor, so kind of ionic doping, can be something that's interesting and enhance the fluorescence. Okay, so let me conclude. So I mentioned the sad long history in some sense of doping, but I think we're making progress. It's related but distinct from charging. Manganese was used a lot as a model impurity, and I want to stress that as far as I know, there's no self-purification. We all love this model, and it's hard to get rid of it, but there's no experimental evidence for it. And now there's a lot of work on electronically active impurities, and where we've been working with silver, which is amphoteric, and it makes this donor to acceptor transition. And also this idea that just a few silver enhances the fluorescence quantum yield. And finally, we're trying to understand not just doping, but also cation exchange more broadly with this microscopic model. So finally, let me just thank the people that did the work. I mentioned Li-Jun Zhu and Ayash and Florian. These are students that did the work. And of course, we had a long-standing collaboration with Steve, Sasha, and Tom Kennedy. So thank you very much for your attention.